First, I would like to thank Hossein Tabatabai for giving the course last week. I had a last-minute emergency due to a sad family event. I had to travel on Thursday, and Hossein agreed to do the course at the last minute, and I believe he did it well. So thank you very much, Hossein. With Hossein, you've seen BGP, and we stopped at this place where we've seen that one of the topics is how does a BGP router put the information it has learned from BGP eventually into the routing tables. And the natural way is to do redistribution into the interior gateway protocol, into the interior routing protocol like OSPF. But very often this is not done because it makes OSPF very big. As we will see later, there is close to 1 million IPv4 prefixes in a backbone internet router. And most of those prefixes are not internal, so that makes OSPF very heavy. So an alternative is that BGP writes directly into the routing table the next hop it has learned through BGP, which is a hack in some sense. It doesn't follow this hierarchical routing idea, but this is a pragmatic solution to this scalability problem. And we have seen that this requires that we do recursive table lookup. The example is that if R4 has a packet to send to this destination, which is an external destination from the AS in the middle, it has been learned by R6 and this through eBGP. R6 has informed R2. So R2 has injected this destination with next hop, the BGP next hop, which is 2222. So that solves the problem for R2. R2 injects next hop into its local forwarding table. And the data packet, when it's received by R2, will be forwarded to R1 because R2 will look up the table, will find next hop 2222, which is not on link with R2. So R2 knows that's a case for recursive table lookup. It will do another lookup and ask the question, how can I get to 222? Now, 222 is an IP address that's considered internal to this domain. Remember that with BGP, all the IP addresses of the BGP peers that are outside, but with whom we peer directly, must be considered internal addresses. So there is a next hop for this destination, and which goes to R1 here. So the packet is sent to R1. Now this packet will reach R1, and the next question is, what happens to this IP packet when it is processed by R1? And that's the topic of the quiz. That's open. That should be open now on Speak Up. Right, do you see the quiz open? Yes. I close the poll in a few seconds. Closing. And the majority says A. It's forwarded to R6 because R1 does recursive table lookup. But unfortunately, the answer is C. It cannot be forwarded to R6. It doesn't work. Why does it not work? Well, because R1 is not running BGP, which makes sense from one viewpoint, because this router is not talking to any external network. So it runs OSPF, but not BGP. Since it does not run BGP, and since there was no redistribution into OSPF of the BGP routes, R1 has no clue about this. It's never heard about this. If there had been redistribution into OSPF, then this external prefix would have been learned by R1 by the mechanisms of OSPF. but this is not the case here. So R1 doesn't know, and the short answer is, well, in fact, it doesn't work. It doesn't work. So doing injection requires recursive table lookup, but this alone doesn't work. In practice, if you do injection, you're required to distribute the information to R1. And how can you distribute the information to R1? Well, by asking that R1 also runs BGP. If you enable BGP in R1, R1 will peer in the internal BGP mesh with all routers that are inside the domain here. So we'll peer with R6 and R2, and we'll learn the information from BGP. We'll do the injection, and this will work here. So this is a very common solution. So most networks that I know of do this thing. So you run BGP in quasi all routers, perhaps not all. There must be stub routers and cases where you don't need this, but in a backbone router like this one that needs to know where to go for every packet, and there is no default rule, then such a router will need to run BGP. This is why we can see BGP working in a router that is not interfaced to any external BGP peers, which seems contradictory, seems paradoxical, and it is paradoxical. It is simply because we do injection instead of redistribution. You could tell me that's a bit stupid. We pushed the problem into BGP. BGP has all the routes here instead of OSPF, and it's true. It is stupid in some sense, so not everybody does this. There are some networks who are careful about dimensioning OSPF such that it can handle all the routes, and it can. OSPF is in principle scalable for a huge number of routes, but that's a very common practice. There are also alternatives. So this is one of the fundamental problems. You run BGP, you ideally redistribute, but then it causes a number of problems. So there are alternatives. And if you think about it, this is perhaps the most reasonable alternative, although that's not the one that's most deployed. It is deployed in one solution called Cyan that we mentioned already once. Cyan is not BGP, but is something like BGP that has been invented by Adrian Perrick of ETH and is deployed in Switch as an experimental network. And Adrian Perrick hopes it will replace BGP. We will see whether it is. As we know, it's very hard to move and replace anything in the internet. But certainly this is better than BGP, because what it does is, in a case like this, it will use source routing. Remember, we discussed source routing. Here, in a specific context, the idea is very simple, because the problem finally is in how do we cross this internal network in order to go to the outside here. And the problem is we don't want to put the 1 million external prefixes in R1. And there's a very simple way, because R2 knows that the next hop is 222. R2 has to run BGP. There's no way R2 can escape this. So when R2 has a packet to send to this final destination here, it knows the next hop is 222. So an obvious thing is to use as a source routing header the intermediate destination 222. Right? So if we put into the routing table next hop 222, and then in principle, this is not directly usable because we need to do recursive table lookup. Instead of doing recursive table lookup, you can instruct your router. We have seen that routers can be instructed in different ways using things like SDN. You can instruct this router to insert the next hop as a source routing header. Now, of course, lose source routing here. So this will mean that we insert as a source routing header in the packet the destination 222. So the job of all the routers inside ASX is to send the packet to 222, which makes a lot of sense because BGP gives us this information. We don't bother having more complexity inside the system. In this form that I said, it is not exactly used because source routing doesn't have a good reputation due to security and performance issues in most routers, but it is used in cyan, which is an alternative to BGP. Something very similar to source routing is called MPLS, and this one is actually used. We will speak about MPLS in 2 weeks in more details. But first impression of MPLS is that MPLS is something similar to VLAN tags that can be used by routers to forward the packet by looking at an MPLS header instead of looking at an IP address. So that's very weird. We said IP is a universal mechanism to interconnect all things together. Well, there is yet another thing. There's also the MAC layer that we have seen. There's IP, and there is also MPLS, and we'll discuss that in all details in 2 weeks. But here, what we can think of is that by putting an appropriate label on the packet, and if all routers inside the domain run MPLS, they will be able to know that the packet goes to 222, and this label corresponds, in fact, to the destination 222 here. So this is more complicated than source routing, but in terms of implementation, MPLS is well implemented. There are high-performance MPLS implementations, and backbone providers do implement MPLS. Therefore, this is an alternative solution that is also deployed. When we do injection, we can have what is called an injection conflict. Let me illustrate this on an example. Same example as here, and we focus on R2. R2 learns about this external route from BGP, BGP running between two routers in the same domain. So R2 learns about this route and injects it into its routing table. Now assume that we do redistribution of eBGP into OSPF. All the examples I gave before were assuming we do not do redistribution, but all cases exist in different networks. So if we do redistribution, we can redistribute everything, which does not make a lot of sense. Typically, we redistribute only the routes learned by eBGP. Redistribution eBGP into OSPF, that means a router that runs BGP and OSPF will put into OSPF all the routes that it has learned from BGP from external peers. So R6 will do that. R6 has learned this route from eBGP. It will put it into OSPF. The point is that once you do redistribution into OSPF, you should disable injection, but for some reason, this is never done. BGP router always puts into the routing table everything it has learned. So there will be both injection and redistribution. Why it is like this is probably the result of trial and errors, of doing things and recognizing there's problems. My interpretation is that when people do BGP, they took BGP not like a higher level protocol that needs to be helped by OSPF, but they took it as a standalone protocol that could work as a routing protocol alone. That's the only way I can imagine why things are this way. So R6 will do two things. It will put into the OSPF RIB, the routing information base, so the topology database of OSPF. It will put this external route. And for example, a default with such injection in the software we use is to add a cost of 20. So from OSPF, it is as if we had a direct link to this with a cost that we attribute to 20 at R6. Now, by the magic of OSPF, R2 will learn a route to this destination and will, of course, put it into the routing table. That's the normal job of OSPF. Now, there is two ways R2 has learned from the destination. The first one from BGP, which contains next hop 222. And the second one, which is written here first, from OSPF, which is the result of the Dijkstra computation. OSPF will compute the shortest path to this, which is connected to R6 with a cost of 20. So I assume on this simple example, the shortest path will conclude that the next hop is R1 East here. And the cost in this example would be 22 here. The route that is put by BGP doesn't have a cost, but the one put by OSPF has a cost. Now, in the routing table, we have two destinations with exactly the same destination prefix. So we have a potential conflict that should not happen in principle. So the way this is taken care of is by adding an additional cost, which is called the administrative distance, which is hardwired. And for example, if this is put by OSPF, the distance is 110. If this is put by iBGP, by BGP learned from an internal neighbor, the distance is 200, which is the case here. R2 has learned about this route by BGP, but indirectly, so with a cost that is put with a high value. And then the result is that whenever a packet is used, matching into the IP forwarding table is according to longest prefix match. That's the theory we've seen when we speak about IP. If there are multiple matches, we look at the one that has the smallest administrative distance, and we ignore the others. So in this case, the route learned by OSPF is the only one that will be used. If for some reason OSPF would crash or the route would be withdrawn because OSPF has a problem or is in a transient, the other one would still exist and could be used here. Whether this is truly interesting or not, I'm not sure, but this is how things are in reality. In my opinion, it's more a way to prevent potential bugs that could arise from unintentionally redistributed BGP into OSPF and not being aware of this injection conflict here. Voila, so this is the ugly part of BGP. This is how BGP interacts in practice into the routers. And that's the part you will be confronted with when you do the lab with BGP here, because we have to put the hands into the details. BGP has about 100 or more different attributes. We will not see all of them. I will just mention some of them. One that's often used is local pref. Local pref is an attribute that is assigned by a BGP router when it receives a route, typically over eBGP, and it is statically configured by the configuration of BGP in this router to express a preference. The simplest is to explain on this example here. You remember there is this BGP decision process that will choose a route by following a number of criteria. For example, shortest AS path. Here, if we want to tweak this order, change this order, because perhaps the shortest AS path is not the one we prefer. This example here is there is a link between AS2 and AS4, but for some reason, we prefer not to use it. Perhaps because it's expensive. Perhaps it uses a cable on which we pay a lot. And if there's a lot of traffic on this, we will need to buy a larger share of the cable. And whereas between AS4 and AS3, it is less expensive. Perhaps also those are ASs that are in countries that don't trust each other. So we prefer to have a link because we put high value to connectivity, but we would prefer to go this way here. This can be implemented in AS4 by putting a local pref here. So when R2, we program all the BGP routers in AS4 to put a local pref, which is higher from BGP announcements that come from AS3 than from AS2. For example, when R1 receives a route from AS2, it will put a small local pref, a value of 50. Whereas when R2 receives a route from AS3, it will put a value of 100. So that's a global assignment you have to do in your AS. In AS4, we have to decide on those rules and distribute all those rules in all the routers here. As a result of this, what will R3 announce to AS4 concerning this prefix here that it has received from AS1 via two intermediate ASs here? I'm closing the poll in a few seconds. And the majority says B, which is the correct answer. Well, the solution comes from the decision process. The decision process is not hardwired. There's not a law that says this is how it should be, but that's how it is in some documents that we can find, and in the software that we use. We see that the local pref is used as a criterion before shortest AS path, which makes sense because I justified local pref by saying if we want to control the decision, supersede the decision that otherwise would be taken. Oops. So in this case, R2, R1, and R3 have two routes, and they have to choose one of them. So R2, for example, if it receives the route from R1, we'll see that the local pref of the one it has received from AS3 is higher, so it will prefer it, and therefore R3 will learn only the route that is preferred, which is the route via AS3. And since the rule, one of the rules of BGP is every BGP router selects at most one route, not two, one as best route. And second, you can advertise only the route that for yourself is the best route. So R3 therefore can advertise only the route via AS3. So AS5 will not know that there is this path. It will only think that there is a path via AS3 to this final destination. So the local pref is a value that is proper assigned to a route when you receive it from the outside, propagated inside the domain, and therefore, and that allows to orientate the rules. There is a more radical way called weight, which is an attribute which remains local to this router. Local pref is local to an AS. Weight is local to a router. That's a hack. That's a way to force the decision process to take a specific route. So if you want to force always a certain route that follows a number of criterion, that satisfies a number of criteria, you can put a high weight to this and it will automatically be chosen here. But it doesn't propagate, so there is no weight attribute in weight announcements. Another thing that is often used is related to dual home system, and it's called the MED, multi-exit discrimination. It is used to, in a case like this, where multi-homing, if you remember, means a domain that is connected to several other domains or to one domain at several points. So here, ASY is connected to ASX with two links here that are perhaps far apart. And here, the intention of ASY is that perhaps because X is a provider, Y wants to use the traffic to get rid of the traffic as quickly as possible. So if there is a packet, for example, from the outside that reaches R2 and goes to R3, it should go inside X to R1 and then to R3, and not the other way around. We want to do cold potato routing here because ASX is our provider. Perhaps there is a link between R3 and R4, but this is an internal link that we would not like to use for example, if there is a web server that's connected here that has a lot of traffic, we don't want to carry these large amounts of external traffic internally. That's a very typical situation that many networks have here. For this, we can use the MED attribute. The MED attribute is an attribute that can be carried over eBGP. We've seen that the local pref is destroyed over eBGP or ignored, if you put it. Here, the MED will not, and a small value means prefer. That's the opposite of local pref. So people could not agree on what a preference means. Here, low value means preferred, and we see here that R3 advertised the prefix 10.1 with a small MED, and the other prefix 10.2, which is here, with a high MED. That means, and R4 does the opposite. So the idea is that when X will receive those two announcements, they will have different MEDs, and for example, there will be two routes to 10.1. one via R3, one via R4, and it's the one via R3 that should be preferred. This is what Y is signaling to X. Of course, Y and X are two different entities. There is no guarantee that X will accept the MED or will follow it. When you receive an advertisement from another device, you can change the attributes or you can ignore the attributes. And inside your domain, you're free to do what you want. But you expect this to be respected if X is truly a provider to Y. So if there is a provider-customer relationship between X and Y, you expect this to be followed. And this is a typical case where MED would be used here. R1 has two routes to 10.2 here, learned by eBGP. One via R4 learned from R2 by iBGP. So we're zooming on R1 here. So R1 has learned this route from eBGP, this one from iBGP here. Which one will R1 prefer? Which one will the decision process at R1 prefer? I close the poll in a few seconds. And the majority says A, which is, of course, the correct answer. That's the goal of the MED, exactly. And if we look up the decision process, the MED will be tested before iBGP versus eBGP. Which is so the decision process here, we'll look up all those things. We see that the MED is tested before, so this will make sure this is exactly taken care of. If there is no local pref and no MED, then the decision would lead to a different rule, and a route learned from eBGP would be preferred, and that would cause hot potato routing instead of cold potato routing, as we want in this case here. What would happen if router R3 crashes? For example, if this dies here, right? Well, if this dies, R1 will learn that the route that it has obtained from R3 is dead, because in BGP there is a keep alive mechanism. Remember that a router keeps only one best route, but it keeps all the candidate routes it has received from all the BGP routers it speaks to. So R1 had a route from R2 that was not selected as best to 10.1, for example, but is in the rib-in of R1. So when it loses the best route here, it will redo its comparison of routes, and then it will select as best route the route it had learned from R2, which is this one here. R2 will also be informed of the route suppression, because R1 will now send this information to R2, and R2 has only one route to 10.1, and it will also therefore select it. The result is that all traffic to 10.1 will now be sent to ASY. Now, if R3 is really physically connected to 10.1, and that's the only connection, that doesn't help a lot, because the traffic, the subnet is unreachable. But if there was another path to 10.1 inside ASY, then this will solve the problem and cover and repair the losses here. So MED allows dual homing in the sense that we have multiple attachment points. We can control whether we want cold potato or hot potato, but we also can use the additional links we have as backup links if anything goes wrong. Let me skip this. Now we have seen that there's a number of criteria used in BGP, but the primary ones are weight, local pref, MED, and then the major rules that a router uses is comparing the AS path length and then also preferring what comes from eBGP over what comes from iBGP. Yeah. And if we combine all those rules together, the question, we hope that BGP converges in the sense that at the end of the exchange of messages, that the exchange of messages does end, because one AS informs an AS about routes, another about other one. But as we have seen, whenever we receive a new route, that may change the computation of the best route, which may trigger a new message to be sent. So a priori, there is a good question to ask is, does this process end? Does it converge? A bit like we have seen that in OSPF, when there is a failure, at the end, everything gets recovered. The bad news is that, in fact, no, there is no guarantee that it will converge. You can easily, in the past, when the lab on BGP was 2 weeks, we did one of the parts of the lab was to show an example where this does not happen. You can have an ASA that prefers B, B prefers C, C prefers A, and A prefers B. You can have a cyclic dependency where everybody wants to send to someone else who in turn wants to send to someone else, etc. So if the graph of preferences has cycles, that may cause no convergence. In practice, you don't expect this. I mean, you prefer to send via A because A is a provider to you, for example. So it's rare that you find a case where A is a provider to B, B is a provider to C, and C is a provider to A. So typically, there's a hierarchy. There are big players that are providers to smaller players who themselves can be providers to yet other players. And then the big players are peers to each other. This is more or less how the internet is organized. So in practice, this happens very rarely. It can happen, but it can happen in particular if somebody in a BGP installation of some network does wrong things by putting local pref or weights that will cause a loop in this set of preferences. Here is another example, which is a bit more subtle, where it is not the absence of convergence. It converges, but the equilibriums can be multiple. There can be multiple equilibrium at convergence. Here, I'm showing this situation where there are 4 ASs, where A prefers B over D. So A prefers the announcement that are received from B over those that are received from D. And a good example is exactly the same. A good reason could be exactly in the same example we discussed a few minutes ago. It could be because the link from A to D is very expensive or has little capacity. Is just used because we want to have as much connectivity as possible. And this is what is truly happening in the internet today. So the peerings between the high-level providers is extremely dense. So quasi-everyone peers with quasi-everyone. So you want to have as rich interconnection as possible, but you prefer this because this is local and perhaps it is Ethernet links that cost quasi nothing here. So A prefers B over D. Therefore, A sets local pref is 100 to all the updates that are received from B here. So let's assume the following scenario. A2, this router, receives this announcement from D here. So that's a prefix. This prefix is received directly from D here. And assumes it received this before receiving anything from B, for example, because A2 has just started, and that's the first thing it receives here, or the process has been restarted here. Then what will A2 do? It's the only path it has to this destination. It will take it as best here. Therefore, it will inform B2 of the same thing. So it will pass into B this information that there is a path to this prefix, which is via ASAD here. Now, B2 will receive other announcements via C to the same prefix, and they are via ASBCD versus BAD. Same AS path length, everything is the same. So depending on whatever tie-breaking rule there is, for example, if we use simply the BGP identifier, it is possible that B2 decides that the route from A2 is the best. So B2 keeps this to this destination, this as best route. As a consequence, B2 will not inform A2 of the route which is via C and D. That's a consequence of the rule that BGP announce only the best routes. Right? So router B2 knows of other routes, but it knows only this one. And since the route is coming from A2, it will not repeat it to A2. So the ASA will route directly via D, and B will route via D here, in spite of the preference. Now, the preference will come into play only if there is an opportunity to receive a message from B before a message from D. So if we have exactly the same scenario, but we change the order, assume that the message from B2 here, message 2, is received before message 1. Then this will be adopted as the best route. The local pref will be put to 100. All systems in A will put 100 to the blue route. And when the red route comes, it will be ignored because it has a lower local pref here, which is the intention. So the intention is that everything goes via C and B, which is what will happen. But we see this intention is implemented, results into reality, only if the order in which the messages are received is such that the blue is received before red. And there it's very hard to be sure that this will happen. So if this does not happen, we will be in the other situation, and this will be a stable situation until there is a failure somewhere. Perhaps if a D1 fails, then this new local prefs will come into play, and those things will be ignored. But if it never fails, or for a long period of time it doesn't fail, or if B2, B1 fail before D1 does, then we will be on this. That's an example where there are multiple equilibria. And there are some that exists. Nobody is really upset, but that shows the complexity of going from rules to the desired equilibrium. So BGP imposes policy routing by a set of rules. And as you probably have experienced in other situations, when you try to automate the behavior of your BGP router or of your smartphone or of your email application by putting a number of rules, then sometimes the interaction between rules can be difficult to predict here. So that's part of the complexity of deploying BGP. Quick additional question. What happens when a BGP router loses its best route to some destination in general? Close the poll in a few seconds. Closing. And the majority says B, which is the correct answer. A is what OSPF does. OSPF repeats its local view of the attached networks. And if this repetition is not periodically received, then we withdraw them. BGP doesn't do that because BGP from the beginning knows it will have to be scalable. So there is no point repeating things that are exactly the same. So it will simply send the diffs, which are additions or withdrawals. So BGP will send a negative message by saying, I have lost this route, and this will trigger the cascade of events, recomputation of new best routes, which may in turn cause a recomputation of sending withdrawals, for example, or updates. So we've seen practically everything on BGP, but as you can imagine, for many practical systems, there's also a huge number of other bells and whistles which were added to fix some problems that were discovered on the field. The first problem is called route flap damping, exactly corresponding to the withdrawal of a route. Assume, for example, there is somewhere in the world a BGP router that has a bad machine or bad software, and the BGP process boots, starts, does its job, and crashes, and restarts, and etc. Of course, why would that happen? Well, we know bugs do happen. Once you detect this happens, you kill the process and you try to and if it does the same again, you reinstall it. But that may happen. That has happened, in fact, in the past. And in fact, transient failures that are recovered cannot be totally avoided. So what happens when there is an unstable BGP router? Well, this BGP router will recompute the neighbors of this BGP router with withdrawal routes. They will say, oh, I've lost all those routes. Perhaps I have no other routes. Therefore, I've lost them. I will inform all my neighbors of the withdrawal. And then perhaps a few seconds later, I will send an update. And then a few seconds later, a withdrawal again. So in fact, that has the same effect as a denial of service on BGP. So this causes the BGP routers to become very slow, very non-responsive. And in the worst case, they might be entirely busy taking care of these instabilities and not doing anything useful. So this has been solved by a mechanism, which is a damping mechanism, which is illustrated here. We add to every route an attribute, which is a value, which is shown, a penalty value that is shown here on the y-axis. And I'm assuming for a given route here, it is withdrawn at this time, then updated, then withdrawn, then added, then withdrawn, then added, etc., which is exactly the flapping scenario that we want to mitigate here. Then whenever a route is removed, we add a penalty to it, and this penalty decays over time, but whenever it's withdrawn again, we add another penalty here. So this route has been withdrawn 3 times, and this penalty has gone above a threshold called the suppressed limit. When the penalty of a route is above the suppressed limit, then we keep the route, but we don't use it. We do as if it did not exist anymore, which means in particular, for the 3rd time here, at time t1, the route has suppressed equal 2 and is ignored, which will avoid the propagation of those oscillations to the rest of the world. Hopefully, sooner or later, the problem will be fixed. So here the route was withdrawn another time, which has affected this router, but has not affected the computation of the best route because this route was ignored, cannot be the best route. And at some time, the problem is fixed, and this route is no longer removed. And by not being removed, the penalty will decay until it goes below the reuse limit, at which time the route flag suppress becomes false and can be used again. So routes that are oscillating very quickly have the flag suppress equal true, and they do not propagate through the network. That's how it is fixed. Another problem that we need to fix is, in fact, because we tend to do injection very often, and if we do injection, we have to run BGP in many, many routers, in fact, not just at the edge of our network, but perhaps in the entire core of the network, which immediately poses a scalability issue because we have the BGP mesh becomes very large. If I have a network that has 100 routers, I need every BGP router inside my network to speak to the external peers, but also to the 99 other internal BGP routers. So that might, with 100, it might be okay. With numbers much larger than 100, it can be a problem. And it's not very efficient if you think about it, because what is the goal of the BGP mesh, the internal mesh? It is to share the information that is learned from the outside. So you can share the information by having every BGP router speak to every BGP router, or you can find a message distribution mechanism that shares this information in a more efficient way by using a letterbox system, for example. And this is what is done with what is called confederation. A confederation is a structure of the IBGP mesh where some routers use as bulletin boards, where when a BGP router has some information it wants to share with all routers inside the domain, it will share it only with one of the internal BGP routers, which is ahead of its local domain here. How this can be done? Well, this can be done by using what is called private AS numbers and using my big domain, splitting my big domain into subdomains, which are handled as if they would be external domains. So here I have a big domain, which is split into 3, and we use eBGP between the subdomains, even though this is all internal to a single administration. But that solves the scalability or mitigates the scalability problem, because now each subdomain is smaller here. This is possible because we have the concept of private AS number, just like we have private IP addresses. If I do this, I need to be able to identify my 3 subdomains, so we'll give them private AS numbers, which of course are translated when we speak to the outside. Voilà, it's time for a break. So let's do a break until 1:15. We have seen one use of private AS numbers into splitting a large AS into multiple smaller virtual ASs. Another use that's in fact more frequent is by stub networks like EPFL. A stub network means a network that's at the end of the graph at the edge of the graph of networks and accesses the rest of the world via one single provider. That's the case of EPFL that's connected to switch. Now, EPFL might still want to speak BGP with switch, and in order to use BGP, you need an AS number. But for the rest of the world, EPFL is always visible as a part of switch. So it's not a good idea to give an AS to EPFL, because that makes the world look more complex than it is. So for cases like this, a client network like EPFL uses a private AS number that is understood by switch. So switch knows this AS is EPFL, but any announcement is not, this is not added in the AS path, for example. Whenever an announcement from EPFL is sent by switch, there is only one AS number, which is the AS of switch here. So the private ASs are not visible to the rest of the world. They are not used in the path here, but they are used whenever we need to run BGP locally here. So the IBGP mesh can be avoided with confederations, but most systems that I know of use an alternative, which is very similar, but avoids using private ASs by using what is called route reflectors. So a route reflector is similar to what I presented before, but does not break the semantic of I versus eBGP. When we use confederation, we're using eBGP internally, which really is very confusing. So if you want to avoid this confusion, you organize your network into groups that are called clusters, and all the clusters, all the BGP routers that are in the same cluster, they speak to a route reflector. In fact, to 2 route reflectors, one as primary, another one as backup. And those route reflectors are the mailboxes, and there is an IBGP mesh between the route reflectors and an IBGP mesh in between, not a mesh, but there is communication from the route reflectors to all the BGP routers that are inside the cluster here. from the IBGP viewpoint, when a router like this one gets a route from this one here, it will be still treated exactly as if there would be a direct TCP connection from this router to that one. But there is not a direct TCP connection. In fact, the messages are simply forwarded by the route reflectors. So the route reflectors are mailboxes. They don't compute best routes. They don't change attributes. They don't do any of this. It is a pure message distribution mechanism. So everything we've said before remains the same. It is just that the way to exchange a BGP message between this and that goes via two intermediate mailboxes, which are the route reflectors here. Now let's have a look at some details in our neighborhood here. I mentioned several times that many providers want to be interconnected to as many providers as possible. The classical way is by cables. Swisscom pulls a cable to Sunrise to interconnect. But this is not the way it's done in practice, because that costs a lot. And because there's a lot of interconnection, what has emerged is what is called interconnection points, things that have a name that terminates in IX. Swiss IX is one of them, for example. Those are companies that rent a basement in a parking lot or something like this and put racks of routers and Ethernet switches. And any company, any provider that wants to peer with other provider comes to this point here. So those are peering points where, for example, all companies that are present in Switzerland are present here and they interconnect with each other. In such settings, in such settings, you may have what is called a route. So this is, for example, what is happening in one such peering point. You have a number of providers. Every provider has a router, in fact, one or a few blades in racks that are your BGP routers. And then you need to interconnect to all the BGP peers you want to have, which is not necessarily every other provider in this room, but is very often quasi all other providers. So because of this, you have eventually in these interconnection points the same problem as we had in the internal IBGP mesh. We have a lot of BGP interconnections. So this is taken care of by having also what is called route servers. So a route server is one BGP router that will play the role of a mailbox. So if I want, as a provider, to interconnect to the 20 different providers that are in this room, I send my messages to this guy who will send it to each of the 20 providers here. The route servers, in fact, are also very useful because many route servers, in fact, publish the information they have. So this is how we can view the messages that are exchanged between providers. The other ones we cannot view. I mean, if there is a private link between Sunrise and Swisscom, Sunrise sees what happens there, Swisscom also, but the rest of the world does not. It's a private affair between those two companies. Many route servers, in contrast, publish what is available, and this is how we get this information here. So those interconnection points, so famous ones are May West and May East. May West is on the American West Coast, May East is on the American East Coast. They are, in fact, the high connectivity parts of the internet. And if they are destroyed, then you might lose a lot of internet connectivity. So they tend to be extremely well protected, and their location is not so well advertised here. We might lose an interconnection point because of an attack, but there are other attacks that, of course, can be done on BGP. In fact, BGP, like DNS, that we will also discuss shortly, are the two important parts of the public internet that may cause the internet to work or not to work. There is a well-known attack, which is called subprefix hijack, which is caused here. Assume this internet service provider is malicious. It could be truly malicious, although there is no really malicious internet service provider in the sense that an organization created by organized crime, by mafia, to be an internet service provider, that does not exist. But there are countries that are malicious with other countries. So this could happen here. So assume ISP3 injects into ISP1, so ISP3 is in the US, ejects into ISP1, the two 16-bit subprefixes of EPFL IPv4, 128.178/16, 128.179/16. They belong to EPFL, but this guy pretends that he or she knows a direct path and informs ISP1 of this here. So the path is ISP3. So this guy is saying EPFL is directly connected to me. Now, if we look at traffic that goes from C1 to EPFL, right? So C1 is a customer of ISP1. ISP1 is a global ISP, AT&T, for example. And there is a packet that has to go to EPFL. Normally, EPFL, which is here, 128.178/15, has injected this into ISP2, which by BGP has forwarded to ISP1 here. What will happen? Will such a simple attack work? Close the poll in a few seconds. Closing. Well, there's almost a tie, but majority thinks that the attack will be successful. And it's probably true. And in fact, it depends whether aggregation is performed or not. Well, let me explain. If aggregation is performed by this ISP, which probably is not the case because the ISP is doing the attack. So if you're not doing if ISP1 is aggregating those two prefixes, ISP1 has received two announcements to this. So if ISP1 transforms those two announcements into an announcement to this prefix, then ISP1 has two. Now, what will happen? Well, if ISP1 chooses the shortest AS path, which is probable here, then the attack will fail. ISP1 still knows another route here, but that route is better and it will go here. However, if, depending on the shortest path rules, if there are equal paths, depending on the complexity of the path that goes here, it might be that this is the shortest path in AS path, and then the attack would succeed here. So if aggregation is performed, we don't really know. It depends on the other elements of the story. But if ISP1 does not do aggregation, then there will be inside ISP1, there will be three prefixes, 1, 2, 3. Remember, with BGP, overlapping prefixes are considered as different prefixes. So there will be three prefixes. This one will be accepted. This one will probably be accepted as well. And whenever a packet goes to EPFL, it will match either one of the red prefixes and the blue. But the longest prefix match means that it's the red that will always be preferred. In the routing table, there will be a routing table entry with a longer prefix than the blue one. So the red one will always match in the routers, which means they will go towards ISP3. So if ISP1 does not perform aggregation of the prefixes, the attack will work. So most of the time, this is what happens. So this is a well-known attack. It's called subprefix hijacking. It was performed, for example, by an Asian country that wanted to ban some access to YouTube. So it did an attack by injecting into its national network prefixes that corresponded to subsets of the prefixes of YouTube. And this was sufficient to prevent all traffic from going from inside the country to YouTube. So that's a form of censorship and the kind of mechanisms that can be used here. Of course, we want to avoid this. One simple way to avoid this is by simply having a database of all the origination, which is called the routing registry. So the internet is self-organized, but there's still an organization of the ISPs. The internet service providers are organized. Per continent, there is an international entity, which is the Regional Internet Registry. For Europe, it is RIPE. You might remember a few weeks ago, there was a RIPE workshop that some of you attended. So this is also serving as a forum for a dissemination of technology and science about the internet in that region. But it also serves as a routing registry, which is a database of all the address blocks, and also contains the policy information that some companies are willing to make public here. So ASS can have access to this, so this is public information, and then you can use it to verify the routes. For example, if ISP1 goes to the Internet Registry of Europe, it will know that this route here is originated by switch and not by ISP3. So it will deduce that there's a problem. ISP3 should not be one AS hop away from this prefix here. That's simply by screening a public database here. It's not cryptographic, and it works more or less well. And what is being developed is a purely cryptographic solution to this, using what is called the RPKI, the Resource Public Key Infrastructure, which is a set of public key certificates, which is rooted at the entity which is the entity that manages the allocation of IP addresses, among other things here. So that concerns the origination of who owns this IP address. For example, EPFL owns the block 128.178/15. So this is known by RIPE, who delegated, in fact, to EPFL this block, and RIPE is known by ICANN. Therefore, it is possible to sign a certificate that certifies that this route belongs to, that this prefix belongs to EPFL. So the certificate is signed by RIPE, and the signature of RIPE can be verified by looking into ICANN. Very similar to what we discussed when we talked about TLS. How do I know when I use TLS and that I'm going to the bank and that the certificate I'm seeing is really the certificate of the bank? Well, I look at the signature of the bank, which is verified, and is verified by an entity, which is verified by whoever downloaded or created the software that I'm using, which is typically your internet browser. So if you use a Safari or Edge or Opera or whatever, this has the root certificates in it. And if you download it by simply buying from Microsoft or Apple, then it's Microsoft and Apple that guarantee the validity of this certificate. Here it is ICANN that guarantees the validity of the root certificates, and then by delegation, the local registries here. With that, so what is called the root origin authorization, that's the equivalent of the certificate for e-banking that guarantees who is the origin of this certificate. So that can be done, of course. There's probably there's order of 1 million such AS prefixes. So there is a recently deployed software, open source software, Routinator, that does it automatically. So you can verify whether a certain certificate, a route origin authorization is correct or not by using this software here. So all routers, modern BGP routers, should implement such a verification by using the software called Routinator. And that's more or less the state of the art today. Beyond this, it is also possible to validate the entire path with route origin authentication. What we verify is that this route is truly belonging to EPFL or to switch, not to another one who pretends to be. That leaves the possibility of changing AS path. For example, in announcement, it is possible for an intermediate AS to modify the normally what an intermediate AS does is select the best route and add its own AS number when it's to the existing route. But you can also modify it. There is no check of this, except if we authenticate not just the origination, but all the modifications that were done to a given path, which is way more tricky, because that means being able to authenticate every message you receive and every modification to every message that you receive. So not everybody deploys it. There are still performance issues in deploying that, but this is partly in progress. This motivates also Cyan to say that perhaps it's better to use me than BGP, because Cyan natively uses source routing and systematic encryption that avoids all those problems. The future will tell whether Cyan is able to be a solution to that problem. Here is a snapshot at one point in time of the switch network. So switch has internal cables, and then it peers. Here we see in 5 locations to other networks here. So that's the type of complexity you can have for such a network. As you see, a small network like switch is peering to a large number of other networks and is peering to some of the networks in multiple locations. For example, it's peering with Swisscom in Geneva and in Zurich. Some companies like Hurricane Electric, which is an internet service provider, are very open. So they give a lot of tools for example, you can use their toolkit to verify a number of things. For example, here you can verify your own IP address, where it's coming from. So you will see this. And here it will say that your address, I have learned about your address through a BGP announcement that is signed and is valid here. So Hurricane Electric is using Routinator and is verifying whether such an announcement is signed and valid. Not all announcements are valid and are signed. If it's signed and invalid, then probably you delete it. If it's not signed, then you still use it. By going to the Hurricane Electric website and their route servers, you can find some information about the size of the internet. Here is the size of the internet as seen from Hurricane Electric. IPv4 on the top, IPv6 on the bottom. On the x-axis is time. You see that in 10 years ago, there was, well, it's not clear what the scale here, but there was about half the number of IPv4 prefixes as there is now. There's been a sharp increase over the last 10 years, and this is flattening. And now there's an exponential increase of the number of IPv6 prefixes. We are close to 200,000 IPv6 prefixes and close to 1 million or above 1 million IPv4 prefixes. IPv4 is not expanding anymore, so we can expect that this will not increase. And we can hope that in a few years we can delete this, we can get rid of IPv4, in which case we have only this. In the meantime, we don't. So a backbone internet router has in its routing table all those over 1 million prefixes, right? That's the complexity of BGP and of IP packet forwarding. In real time, you need to look up, do a choice between 1 million possible destinations. That's the size of the internet today in terms of prefixes, in terms of ASs, so autonomous systems that are visible by Hurricane Electric. For example, EPFL is not visible. EPFL is seen as switch. We are close to 40,000 systems that do IPv6 announcements, and about twice as many who do IPv4 announcements here. So there is still a large number of ASs that do not announce any IPv6, right? About half of them, which means IPv6 is still not the dominant protocol in the internet. Voila, that's about BGP. Security of BGP, we have mentioned a few things. It's, of course, an active area of research and development. And I've mentioned several times Cyan, which is hoped to be an alternative to BGP and keeps essentially the same ideas, but makes it in a more efficient way with systematic encryption and source routing embedded in all routers to solve the problem, for example, of redistribution that no longer is needed, and natively solves the problem of security. The future will tell whether this displaces BGP or not. That's the end of the module on BGP. Without further transition, we jump to the next module, which is pompously called application layer. I said pompously because, in fact, we will speak very little about the application layer software itself. The application layer, which is the top layer in our construction of the internet, is not the main focus of this course. It's the focus of distributed systems and a number of application systems. And you find it from all completely huge systems like Facebook, that is, and Google, which are YouTube, which are perhaps more than half of the internet traffic today. And very simple systems, like, for example, if you want to watch a movie on your home system, then you have a local area network application layer. What we will discuss is the parts where all the networking zoo of things, transport, IP layer, etc., where they interact somehow with the application and they become visible, and the other way around, where the application layer somehow interacts with the interconnection layer. That's really the focus of this one here. You did an application layer program in Lab 3. Your socket program was, in fact, an application layer. So you needed to specify what the server is expected to do and what the clients are expected to do. And writing the code is, of course, the fancy part, but that's not the one we focus here. But let's say a few words about how the application layer uses TCP. So the web typically uses it with HTTP. We are now at version 2. Version 3, we'll say a few words about it in a second. The HTTP 1.1 uses one TCP connection per object. That was to make things simple, but people quickly realized that makes servers very heavy. So in the next version of TCP, there was a decision to use the same TCP connection for several objects here, which made HTTP2 very complex, because then the server had to multiplex multiple objects onto the same socket. Objects are, for example, the scripts that are on a web page, the graphical elements, etc., the JavaScripts that are sent to the client, etc. So all of those, when you use HTTP, can be multiplexed. Also, you can have active pages, for example, where the server is sending a refresh of the page. All of this can be done with HTTP2 over a single HTTP connection. With HTTP 1.1, it was the other way around. Every object had to create a single connection, which made the web server very simple, because when the web server had to send something, it would do, like in Lab 3, send to the client, which was easy. Whereas here, it needs to, for example, if it has 10 objects to send, it has to do a scheduler. It has to do which object do I send now into my socket. So it needs to do part of the work that the operating system is doing for you when you use multiple sockets. The application layer has to do it. Let's discuss some of the side effects of doing this. I'll let you discover the fairly long question that's here. I close the poll in a few seconds. Closing. And we see a perfect tie between A and B. And the correct answer is B. Because when the server, so when I say first object, I mean the object that's considered first by the server, is sent over the HTTP connection, over the TCP connection, then the second one. Then remember, a TCP offers a streaming service. It insists on delivering the bytes in the order that they were sent. So if one packet of the first object is lost, TCP will detect the loss, will retransmit it. But on the destination socket, the rest has to wait until this loss is repaired, which means object 2 has to wait, which is embarrassing. You're displaying a web page. There is a graphical logo on the top of the page. Then one byte or one packet of the logo got lost. The rest of the page will not display until this is repaired. And the logo was completely useless. You would have preferred to receive the page entirely and perhaps see the logo later. So, of course, one way to do it is as a server designer, as an application program designer, you have to know this. So you want to send first the things that are more relevant, that require immediate interaction. So if you have logos and graphical elements, you have to find a way that your web server will not treat them as first object, but will give less priority over sending them so that your page will first display without images, for example, and the images will graphically, will come. That's the consequence of TCP being the way it is here. Let me skip this question here. This is exactly one of the motivations for doing an alternative to TCP, which is called QUIC. I put QUIC in the application layer because it's convenient to do it at the end of the course, but it's really transport layer. But our transport layer is already big. There's TCP, UDP, there's congestion control. Now there is QUIC. Well, but that's how things are. Formally, I call it application layer because QUIC uses UDP. So if we want to be strict, stupid, and formal, anything that uses UDP is an application. So QUIC is an application. The reality is QUIC is a replacement for TCP and TLS at the same time. Right? That wants to solve two things. The first thing is the one that we have seen in the quiz, to try to avoid this problem of head-of-the-line blocking. Head-of-the-line blocking is the name that is often given to this behavior of TCP that offers a streaming service. If anything is lost, then we are blocked by what the first thing that is lost, and sometimes it's not a good idea. The other thing, perhaps more important in the motivation of the QUIC designers, was security. The other motivation is security. We can today use HTTP without TLS. We can use HTTP over TCP. In fact, this is how HTTP was created back in the 90s. 92, there was no TLS. So the web servers, believe it or not, they were HTTP, not HTTPS, which seems completely weird today, but this is how the world was seen by computer scientists in the beginning of the 90s, at least the ones working in academia. Now, of course, if you use HTTP, you must use HTTP over TLS. We've seen in Lab 3 and in the module of the transport layer that we need to have those SSL sockets that will wrap the TCP socket by adding the cryptography, which if we look at the messages with Wireshark, we will see first we open the TCP connection, then we open the TLS encryption, which causes 2 round trips, at least 5 messages, and those 2 can be sent close together or even together, but we need at least 2 round trips. That means that before opening a TCP connection to do anything useful with TLS, we need 2 round trip time here. That is one of the things that QUIC is trying to fix. Because of latency, that's one of the constant concerns of Google. Google is very concerned with latency because when you do a Google search, if you don't get the reply immediately, perhaps you will do something else. And so the response to a Google search fits in one page, so it's really truly interactive traffic. So latency is an issue, And this was one of the motivations. The other motivation is to say, well, we always do TLS with TCP, so why don't we do the two together in the best way? And in particular, could we have something that would fix the issues of TCP ahead of the line blocking here? But while doing this, an alternative would be to modify TCP. But another thing, which is sometimes called the fossilization of the internet, it is quasi impossible to modify TCP, at least in the sense of radical adding options, because there are so-called middle boxes that play with TCP. We have mentioned very briefly this when we said that TCP has a problem. TCP has many problems, head of the line blocking. Another one, in terms of congestion control and fairness, is bias against long round-trip time, which is mitigated by cubic when cubic works in the cubic domain, which is very rare. You work in the cubic domain where you're transferring gigabits per second, which you seldom have. So in practice, you always have the problem that TCP is unfair against connections that have long round-trip time here. And this is a very serious problem that, as I mentioned, makes it quasi-impossible to download content from very far away in the internet over a wireless link. So to solve that problem, we can do what is called transport application layer gateway, that we'll discuss in a few more minutes, or what is called TCP intermediate system, which is deployed by cellular service providers. So when you send data, they will analyze your TCP header and send an ACK back to you, pretending that this packet has been received, even though it has not been received. And then they will put a server in the middle that will be a proxy for you and will try to download it from wherever you're downloading it. So they break your TCP connection into two, and they play with your TCP connection. So if you have box like this, of course, if you modify TCP, then you have a problem here. And also many routers, like routers that protect domains against various attacks, will discard any TCP packet that doesn't look familiar. So if you do something new, you need first to wait until all those machines have been upgraded to know of this new development of TCP. Whether this is a good reason or not is not 100% clear, but the consequence of that is that when this was started by Google, when Google decided to modify TCP, instead of modifying it, they created something on top of UDP. So it runs over UDP. By running over UDP, it works everywhere. If your cellular network does an optimization of TCP, it will not touch your UDP flow. So you will not be optimized, but you will not be broken either. So it runs over UDP, which means it does not run always very well if you run a cellular network, because perhaps the TCP optimization that are done by Swisscom for you will give you a better performance than QUIC. But the hope is that sooner or later, Swisscom will have to do something for QUIC. And the major change is that QUIC always works with TLS. Always works with TLS. That means, in fact, when we use QUIC, we first establish a TLS session. Whereas with TCP, we first open a TCP connection, then we agree about the cipher and the cryptography. Here we do the other way around. First, we agree about this cryptography. We do this over UDP. That means this exchange needs to be to have something like the stop-and-go protocol to make sure if the packet is lost, we resend it, etc. But we refuse to do anything before setting up the security association here, which makes a lot of sense. And we should never go to a website that is HTTP alone. I mean, perhaps it's something that is so old, a website that has been done 25 years ago by a university professor somewhere who has his own server at home and never modified it. That might be the case. But if that's the case, you can safely ignore it. Otherwise, it's probably an attack. Somebody is trying to do an attack on your system. So first, you will do the TLS3 1.3 handshake. And after that, well, the other thing is that the magic of Quick is that once you have done this, well, you have this equivalent of the SYN and ACK. So, because why did we have this handshake at the beginning? Well, the primary goal is to synchronize the sequence numbers to make sure we know what number 1 means and making sure we know where things start here. But if we are able to agree on a crypto cipher, then we're able also to agree on lots of other parameters, among which are the initial sequence number. So this becomes useless if we do this first. So this is the main observation. Then there are other things that this is doing. This is agreeing on the MSS, maximum segment size, the maximum packet size that can be seen as by TCP here. And avoiding, for example, things that would not work. But here, Quick assumes that we must work with at least this minimum packet size, which is large enough, which is supported by quasi all systems. So if your system does not support such a packet size, you cannot use Quick. End of the story here. So Quick is a replacement that is implemented in all Google apps. So if you have a Google app, YouTube, for example, or Chrome, or web browser, then it will use Quick. It will also use TCP, because even if you're using Chrome, you might go to a web server that is not supporting TCP, Quick. So it will first try with Quick. And then, for example, YouTube will typically first try with Quick. And if it works well with Quick, it will continue with Quick. If it doesn't work, for YouTube, the reason is not that the server does not support it, because obviously the YouTube servers support Quick, but there might be boxes in the middle that don't accept it, that kill, for example, your UDP packets because they don't like it, or simply that the performance is very bad because you don't have the performance optimization you had with TCP. But this tends to disappear, so Quick is really displacing a lot of TCP traffic. With one major change that is solving the head-of-the-line blocking, is that Quick allows to have multiple streams. TCP offers a streaming service. And if you want multiple streams with TCP, you have to open multiple TCP connections. And if you use TLS, you will need to do multiple TLS over TCP associations, which is adding complexity linearly with the number of connections. With Quick, you do it the other way around. First, you establish a TLS association. Then you can do as many streams as you want within this association, and there is no overhead in creating a stream. In fact, a stream is simply a number in a field in a header. And so if you send packets over a Quick connection, if you want to create another stream, you simply change the stream number, that's all. There is no specific setting up of a stream here. So streams can be created and deleted on the fly. So HTTP over Quick, which is called HTTP3, will, of course, natively be able to use multiple streams. So if you're designing your web server application, you will use different streams for the different elements of your web page. And then you don't need to worry about which stream is, which object is the first, which object the second. You simply do as many streams as you want here. A Quick packet contains multiple frames. So if there is always a stream 0, which is a stream that is used by the TLS cryptographic handshake and for the management of the TLS session. And then there are as many non-zero streams as you need for data here. So you can have inside a packet multiple streams. Now, if a packet is large, if the packet needed by a stream is large, there will be only one stream. But if you have parts of a packet that can be, if the data of a stream is small, you can have multiple streams in a given Quick packet. Of course, Quick will also try to avoid fragmentation. It will not create packets that are larger than the end-to-end MTU. That will be negotiated also at the beginning of the Quick session. The Quick uses retransmission like TCP, but the retransmission is per packet, not per stream. So if I lose a packet, I might affect several streams, and Quick will try to retransmit this packet. Some streams might be affected, some streams might not be affected, and the streams that are not affected will continue to deliver data. The ones that are affected will be blocked, like TCP is blocked here. So Quick obtains reliability similar to TCP. In fact, Quick imitates and implements exactly all the algorithms that we have seen with TCP. Fast retransmit, timeout, and a few optimizations that we have seen here. In fact, it's better than TCP because now the ACK frames, which is all the overheads of TCP, which is contained in the TCP header, which is present in every packet. Instead here, it's contained in stream 0. So you can put whatever you want in stream 0. It's elastic. You don't need to burn a big header in case you would have large information to send. For example, if you have a lot of losses that are sparse, you can have a large number of selective acknowledgements, whereas in TCP, we had only 3. So those are small, minor improvements here. Flow control is the same as TCP. Remember, flow control is about preventing the receiver from obtaining too much data. So flow control is done by the window flow control in TCP and adjusting the size of the window. So here it's done in a very similar way. And but it doesn't use a window. It simply gives an explicit offset. So it is saying, I am ready to receive all the bytes from this number, not more. And congestion control is performed exactly the same as in TCP. As far as I know now, there are 3 implementations of Quick, one the original by Google. There's more than 3. There's the original implementation of Google. Then there is the reference implementation of Google that is made open source. And there are implementations by Facebook and Apple. Each of those uses a different variant of congestion control. The standard, so Quick is being standardized, and the standard implementation of congestion control uses TCP Reno. Reno means we do additive increase, multiplicative decrease. We do that per connection, not per stream, which makes sense. We want to control the total traffic going from A to B. If there are 20 streams for ease of displaying my web page, we should not have 20 connections. So we have only one connection, and the traffic on this connection is controlled globally. I will conclude and steal 2 minutes of this by showing you the kind of things that can be done with Quick. This was a master thesis done at EPFL a few years ago. In the context of the smart grid, you remember one of the problems, the TCP is head-of-the-line blocking. If you have a sensor application that is sending data every 20 milliseconds, you want this to be sent reliably. So you want to use TCP. But you don't want to use TCP because if one packet is lost, TCP will stupidly retransmit, whereas perhaps there is a fresher packet that should supersede the obsolete information. This can be very simply done with Quick by creating one new stream for every packet that is sent. So the sensor, when it has new information to send, it creates a new stream, and this is done simply by incrementing the stream number. Of course, you cannot have millions of streams, so you do the stream number modulo some number, which is large enough so that you don't have problems. So every measurement is sent in one reliable stream. So if this packet is lost, Quick will try to retransmit it. But if it is if the loss is not repaired before another fresher measurement is sent, then the Azure measurement will not be blocked and will be delivered at the destination. Voila. Thank you for your patience for the 2 minutes of overflow. And that is all for today.